Hello, welcome to another exciting chemistry uh, program. This is your host, Mr. Mansa, your chemistry tutor. So today we're starting a new series on mole concept. This is a very exciting and very interesting, detailed topic in chemistry. We'll be looking at different calculations in terms of mass, in terms of moles, in terms of empirical formulas, and concentration, and so on and so forth. So to start with, we're looking at the learning objectives. So by the end of this series, those are the expected uh, objectives that we need to know, or we have to know. So for today, we're going to start with the description of relative atomic mass and relative molecular mass. So to give more details about this, allow me to start with the introduction. Allow me to start with the introduction. Right. So we're looking at the relative atomic mass and the relative molecular mass. Alright. Right. So there is need for us to understand where the relative molecular mass comes from and how to relative atomic mass and how to derive and how to calculate. But before we do that, allow me just to briefly talk about the introduction of where or the inspiration of more concept. So chemists for a long time have been interested in knowing the quantities of substances they are dealing with. So when you're about to perform an experiment, there is need for you to take stock of the quantities that you have and probably calculate how much of the expected yield before the actual experiment is conducted. So you have an idea of how much products you're capable of getting in a certain reaction. So there was an interest uh, in terms of knowing the quantities of substances that people are dealing with. So for example, how many atoms, molecules, mass of the compound, or ratios in which atoms combine. So you want to know the proportions in which certain elements combine to form a particular compound. So in short, chemists needed a unit of measurement. So there was no unit of measurement, but there was a challenge. The atoms are so tiny and their masses are almost negligible. So the masses are very, very small and it's very difficult for you to measure. So this problem was, however, solved after discovery of an equipment called the mass spectrometer. So the mass spectrometer is an instrument capable of measuring precisely the atomic masses of elements. So it measures the atomic masses, the tiniest mass. This machine is able to pick and measure. So talking about the background of the relative atomic mass. So as earlier mentioned, atoms are very tiny and their masses are also extremely small in value. For example, the mass in grams of one atom of hydrogen is 1.4 times 10 to the power negative 24. So you can imagine how small that number is and how it could be very difficult for you to measure that particular number because it's very, very small. So to obtain such a mass of an element and use it in calculating quantities of elements, being used in an experiment is very cumbersome. Because of this, chemists found it convenient to adopt one particular unit of mass and compare how many times heavier or lighter the atoms of the other elements. So at this particular point, chemists needed a standard or a reference standard point where to compare all the elements to. So initially the mass of an atom of hydrogen, so initially hydrogen was used as a standard. Every element was compared to hydrogen. So that is basically what they're trying to explain in this statement. Therefore, to get the relative atomic mass of an element, the mass of its atom is compared with that of hydrogen. So below is just the formula that they used to use, and the relative atomic mass is abbreviated uh, by this. So capital A subscript R, that is the relative atomic mass. So they used to use the mass of one atom of an element, then compared to one atom of hydrogen. So what that simply means is that an atom of oxygen has a mass of 16, which is 16 times heavier than that of hydrogen because hydrogen is 1. When you go to carbon, carbon will be 12 times heavier than hydrogen. In 1961, according to the UPAC, which is the International Union of Pure and Applied Chemistry, they chose carbon atom to be a standard. So now every element was being compared to standard, and that is where the relative atomic mass stands even at this point. So we get the mass of an element, and it is compared to 1 over 12, which is just the mass of 1 over 12 mass of one atom of carbon at the moment. So I'm sure there was an error. Here in this book. So this is supposed to be 1 over 12 the mass of carbon. 1 over 12 the mass of carbon, like it is mentioned in this statement. So 1 over 12 the mass of carbon, not hydrogen. So carbon at the moment stands as a reference point. So everything is compared to carbon. So when you check hydrogen, the mass is 1. Therefore, it's 1 over the mass of carbon, which is 12, as heavier as that standard of 12. Magnesium is twice as heavy as the standard atom because magnesium has the mass of 24. So the 24 divided by 12. So that is where the twice is coming from. So it's 2 times heavier. What about potassium? So potassium, the mass is 39 divided by 12. Then you will be able to tell how much it is heavier than. So basically that is the introduction of the relative atomic mass. Now we have a job to calculate the relative atomic mass of isotopes. What is an isotope? An isotope is an atom of the same element that have the same proton number but different mass numbers. So allow me to switch and look at this right? So we've talked about the definition of the relative atomic mass. So this is the mass of one atom of an element compared to 1/12 the mass of carbon 12, and it is denoted by capital A subscript R, and it doesn't have units because it is a ratio. It doesn't have units. So we have what we call the relative atomic mass of isotopes. So using the mass spectrometer, it happens that you run a certain sample of an element. For example, the common one is chlorine. When you run chlorine in the mass spectrometer, you're going to get two isotopes. In this case, we're going to get two isotopes of chlorine. That is chlorine with a mass of 35 and chlorine with a mass of 37. So basically that is what we are looking at here. So we have chlorine with a mass of 37, chlorine with a mass of 35. Now, on the y-axis, we're going to have what is known as the percentage abundance. The percentage abundance. So when you run this chlorine sample in the mass spectrometer, the chlorine 35 gives you the percentage abundance of 75, and the chlorine 37 gives you the percentage abundance of 35. So your task now is to calculate the relative atomic mass of these two chlorine atoms. So how do we calculate? So this is where the formula comes in. So this is where the formula comes in. So when we go up, we have this formula. So this formula is dependent on the number of isotopes that you have. So you can see here we have the relative atomic mass denoted by the capital A small letter r, and then this is the formula. So the percentage abundance of element 1 divided by 100% times its relative atomic mass. So if this is chlorine, we'll look at the example. If this is chlorine 35, when you run it, it will produce its own percentage abundance that you're going to substitute here, and then this mass goes there. Then we're going to have another chlorine, so chlorine 37, which will have its own percentage abundance, and then this is what goes there, and then the relative mass goes there. So if it happened that we had another chlorine, so the calculation continues depending on the number of isotopes that you have. But in this case, we limit ourselves to just two isotopes. So the requirements, you need to know the percentage abundance of an element, you need to know the relative atomic mass of that particular element. So let's quickly look at the example. So in the example given, we have the figure below shows the graph showing the isotopes of chlorine, calculates the relative atomic mass of isotope of chlorine isotope. So we have chlorine 35 given as a percentage abundance of 75, and chlorine 37 given as a percentage abundance of 25. So how do we calculate? So we start by stating the formula. So percentage abundance of chlorine 35 divided by 100% times percentage abundance of chlorine 35, which is its mass, plus, so there is a plus sign. Let me just use highlight. So there is a plus there. Then percentage abundance of 37 divided by 100% times the relative atomic mass of chlorine 35. So substituting in the formula, so we have 75% and then the chlorine 35, 25% and then the chlorine 37. So once you do that, you get these two values, and adding those two values, you get 35.5, and this is what we see on the periodic table. So this is what we see on the periodic table. So that happens to be the relative atomic mass of chlorine. That is what we see on the periodic table. So basically that is how we calculate the relative atomic mass of isotopes. Just look at another example so that we just get familiar with the concept. We are given to calculate the relative atomic mass of isotopes of bromine. So we have 50% percentage abundance of bromine 81 and 50% abundance of, so we have bromine 31, 50%, then we have bromine 50% and 79. So it's just a matter of substituting. So 50 and 81, then 50 and 79. So that will give us 40.5, 39.5. When you add the two, you get 80, and that is what we see on the periodic table as the relative atomic mass of bromine. So basically that is how we calculate the relative atomic mass of isotopes. Know the percentage abundance, know the relative atomic mass of a given element. Then to proceed, we're going to look at what we call the relative molecular mass. So relative molecular mass. So relative molecular mass is the mass of one molecule. So just the mass of one molecule. What is a molecule? I believe we know the meaning of a molecule. So the mass of one molecule, and it's also compared to the reference, which is 1/12 of carbon atom. The relative molecular mass is defined as, it's just the sum of the relative atomic masses. So the relative atomic masses are added together in a certain molecule. So if you look at the molecule, their relative atomic masses are put together. So we have the relative molecular mass and the relative formula mass. One which looks at the molecules and one which looks at just the formulas, the chemical formulas. So we have to know a molecule. Relative molecular mass is denoted by, so we use this capital M, small, subscript R. So it's pronounced as Mr. in most cases. So relative atomic mass is A R, relative molecular mass is M R, and it doesn't have units. How to calculate the relative molecular mass or relative formula mass? If you're given a molecule, you calculate for a molecule. If you're given a formula, it's relative, but it's the same principle. It's the same principle. So before we proceed and learn on how to calculate this, there is this important component that we need to understand. This is a very important component that we need to understand, because this is what will help us. So there is need for us to know how to determine, let me put formula. Right. So there is need for us to determine the number of atoms. We need to know how many atoms are present in a given molecule or in a given formula. So for instance, you're given hydrogen. How many atoms are present in hydrogen? So the interpretation is that you have two of the hydrogen. So it means that you have two atoms in hydrogen. What about water? So water is H2O. How many atoms do you have? So there is one oxygen and there are two hydrogens. So when you add, you find that you have three atoms. This is a very important concept to understand. So there are three atoms. Let's look at ammonium carbonate. Ammonium carbonate. Ammonium carbonate is NH4 brackets 2CO3. So here you have how many oxygens? 3. We have a carbon there, which is 1. We have a hydrogen there. So a hydrogen, these are in brackets, meaning that they are affected by a 2. So whatever is in brackets, whatever is inside should be multiplied by the 2 outside. So it's 4 times 2, meaning you have 8. Then there is a nitrogen, which is 1 inside, so 1 times 2, you have 2. So when you add together, you find that you have 14 atoms. So there's a reason why this will help us to calculate the relative formula mass or the relative molecular mass. Let's look at copper. So this is SO4. So this is called hydrated copper 2 sulfate. Hydrated copper 2 sulfate. Hydrated copper 2 sulfate. How do we calculate? So we have how many oxygen? So there's a 5 in front. Let me just use a different marker. There's a 5 here, meaning that this 5 affects everything. Therefore, you're going to have 5 oxygens. Then 5 times 2, because you have 2 hydrogens already, so times this 5, meaning that this becomes 10. You come here, how many oxygens? So we have 4 oxygens, and there is 1 sulfur, there is 1 copper. So add, it's 10 plus 6, 15. 15 plus 4, 19. Then 20, 21. So you have a total of 21 atoms in hydrated copper 2 sulfate. I hope that is very clear. So the idea is to identify every individual element in a molecule or in a compound. So identify every individual element. What is the meaning of every symbol in that formula or in that molecule? So then it will help you to know how many atoms are present. So to proceed, we're going to learn how to calculate or how to determine the relative molecular mass. Remember, we are on the relative molecular mass. So those are a few steps that you can follow. Determine the molecular formula of molecule, determine the number of atoms that are present, then use the periodic table to determine the atomic mass of each element. Then multiply, this is the key, multiply the number of atoms of each element with the atomic mass. And then you add the values together. So let's look at how it's done. So we'll start with the hydrogen. How do we find the relative molecular mass of hydrogen? Relative molecular mass. So remember, we are on the relative molecular mass, which is abbreviated as the Mr. So relative molecular mass of hydrogen molecule. So hydrogen molecule, identify its formula. So it's H subscript 2. So what does that mean? So H subscript 2 means that you have 2, but this time we are multiplying this 2 by the mass number of hydrogen. So when you go on the periodic table, you find that the mass number of hydrogen is 1. So this is as good as 2 times 1, then it will be equal to 2. Remember, we don't put units, so that is the relative molecular mass of hydrogen. I hope that is clear. Let's look at water. Let's look at water. So water is the second one. So what is water? The formula is H2O. How do we calculate the relative molecular mass? So water, H2O, we have how many atoms? So 1 times. What is the mass of oxygen? So when you go on the periodic table, you find that the mass of oxygen is 16. So this will be multiplied by 16, and this will be 16. We go to hydrogen. How many hydrogens do we have? We have 2 times. What is the mass of hydrogen? That is 1 on the periodic table. So 2 times 1, this will give us 2. Then we add the two numbers together. Therefore, we get 18. So 18 is the relative molecular mass. 18 is the relative molecular mass for water. Let's look at ammonium carbonate. Let's look at ammonium carbonate. So ammonium carbonate is NH4 close to CO3. So calculating, this will be 3 times, what is the mass of oxygen? 16. So that will be 16 is equal to, that will give us 48. We go to, there's a carbon there. So 1 carbon, because we have 1 carbon, times the mass of this is 12. So that will be 12 there is equal to, this will be 12. We go to hydrogen. Hydrogen, we have 4 times 2, so we have 8 times, what is the mass of hydrogen? So its mass on the periodic table is 1, so that is 1 is equal to, give us 8. Then we go to nitrogen. So nitrogen, how many do we have? So there's a 2 here, meaning you have 2 of them, times, what is the mass? When you go on the periodic table, you find that this is 14. So that will be 14. Then this will give us 28. Putting them together, so this will be 8 plus 8, 16 plus 8, 24 plus 2, 26. So you put 6, remain the 2. So this plus this 6, 7, 8, 9. So 90, 96. So 96 is the relative formula mass of ammonium carbonate. So you can try out for hydrated copper 2 sulfate. So this one, the formula is CuSO 4.5 to O. So you can try out for copper 2 sulfate and see the relative formula mass that we are going to get. So just rolling down, you will notice that that is how it gives you step by step how you're supposed to calculate until you get to the final answer. So you will notice that for water we got the relative molecular mass of 2, and then going down for water we got the relative formula mass of 18. Going down for ammonium carbonate, following the same procedure, you notice that we got the mass of 96. So you can try out for hydrated copper 2 sulfate, which I'm sure you did. So let's just compare the answer. So copper 2 sulfate, those are the respective masses for copper: 64 sulfur, 32 oxygen, 16 hydrogen, 1. So when you put them together, you're going to get 250. 250. So basically that is how we calculate the relative atomic mass of isotopes and the relative molecular mass of formulas and molecules. So that's it for today's segment on the series of more concepts. Looking forward to your responses on how the lesson was. If there are any questions, feel free to type in the questions as under the comments, and I will address those comments. So this has been your host, Mr. Wansa, chemistry tutor. Until next time, bye bye.